Thank you, Amos. So, with immense pleasure, I introduce my friend and well-wisher, Dr. K. Jayabal. Dr. Jayabal has completed his PhD from IIT Madras and a postdoctoral fellow from Technical University Dortmund, Germany. He is currently working in the Department of Mechanical Engineering at the Indian Institute of Information Technology, Design and Manufacturing, Kancheepuram, Chennai. He has more than 20 years of teaching and research experience. He published about 30 publications at reputed international journals and international conferences. He authored one book chapter on Encyclopedia of Structural Health Monitoring, published by John Wiley, UK. He also carried out 100 projects worth 70 lakhs rupees, and he also signed MOU with the National University of Science and Technology, Moscow, Russia. He played many roles like Board of Studies member, Anna University, Guindy campus, and a syllabus committee member, session chair, etc. Uh, it is an honor we have Dr. K. Jayabal with us. Thank you, sir, for accepting our invitation. The session is yours now.
Okay. Thank you very much, Professor Murugan, for giving me the opportunity. Am I audible clearly?
Yes, sir. Yes, sir. Clear, clear. Your voice is clear.
So, first of all, I would like to thank. Thank you. First of all, I would like to thank Professor Murugan and the team for giving me the opportunity. So, I just close the video so that less data will be transferred. Then we can directly proceed to the talk. Is the slides visible, Professor Murugan?
Yes, sir. Yes, visible.
Yeah, thank you. Yeah. Today's talk is related to advanced finite element methods. First of all, before I start the talk, my apologies for 10 minutes delay. Primarily, it is because of me due to net connectivity issues. So here, anyhow, you don't worry that I will be completing on time. This 10 minutes delay will not be extended beyond the finishing timeline. And so far, I learned from Professor Murugan that you have been learning the finite element method. Some of you would have already learned it. Some of you may be learning for the first time. So by now, you would have been exposed to the various fundamentals and the concepts necessary for the finite element methods. So in today's talk, we are going to see a advanced topic. So in the advanced topic, we are going to see what is advanced finite element method. There are several such approaches are there. We are going to specifically choose one such approach called polygonal finite element methods. But in the title, it is given as like applications, the finite element analysis and its applications in engineering. That means we have to find an application for the finite element method. Otherwise, it is simply a numerical tool. So to demonstrate the use of finite element methods, probably some applications would have been shown to you using the finite element method. So similarly here also, I divide this talk into two topics. One is like the polygonal finite element method. The second is the application. But actually, to draw more attention from the participants, what I do is I'm going to first present the application. That means where we are going to use it, and then I will be introducing the polygonal finite element method. That is the advanced finite element method, so that you will be able to relate it. Either we present the polygonal finite element first and then go to the application, or first we see where it could be used, then we are going to explain it. So the first what I will do is I'm going to take the application, and then where why we need to the polygonal finite element. So this slide shows the campus of Indian Institute of Information Technology Design and Manufacturing, Kancheepuram. It is a centrally funded institute. Like IIT, NIT, the triple ITs are unique in their own existence, like combining the IT into the engineering. So, the IT is brought into design and manufacturing, and it's a relatively young institute as compared to the other IITs, established IITs and NITs. We have been into existence for about 13 years, and these two pictures show the campus in a long view. And we offer a BTech program, master's program, and a PhD program also. And we have tied up with the several universities abroad. And primarily our focus is on design, so pattern making, patent, and then we have the incubation cell and so on. So these are the some overview about our institute. Now let us get into the topic, and where I'm going to introduce this polygonal finite element is in a smart material. So uh, the conventional materials uh, are known to us, but we are going to bring in the smart materials which are slightly different from the way the conventional materials behave. So here, where we use the smart materials is in the smart system we are using them. For example, we have a control unit, and then there is a sensor and actuator. So when the sensor senses the changes in the environment, it will send the signals to the control unit, and the control unit will give the appropriate signals or necessary input to the actuator, so that the actuator will be performing the desired work. So here you can see again there may be a couple between the sensor and the actuators also, but anyhow we can see the sensor, control, actuators are the three integral part of the system. It is very similar to our human body, like we have like a tactile sensing, and then sensory nerves we have, and immediately send the signal to brain will be sending the signal to the muscles to perform certain operations. No, it is very similar to that. And then the smart materials, no, they we have several smart materials, and then shape memory alloys, which is shown here, and then the piezo ceramic, which are nothing but the piezoelectric materials and magnetostrictive materials. And every other day we see a new smart material is invented. So smart hydrogels, dielectric elastomers, so many smart materials are invented. So these smart materials are used for both sensing and actuation applications. Smart materials are different from the conventional materials. So this slide explains clearly when you can call a material as a smart material. See, here we have the input fields given in this column. Okay, okay, row wise. The outputs are given in the columns. For example, input is like, let us take the third row, stress. So let us take the third row, stress. So let us take a steel, for instance. So we apply stress. What we will get is the strain, so which is also given in the third column. So the input belongs to mechanical field, output also belongs to mechanical field. So both input and output belong to the same domain. That means mechanical domain means, then we call it as a conventional material, and they are related by the elastic constant. We know that sigma equal to E times C epsilon. So E is the elastic constant which connects stress and strain. Similarly, if we take the first row, input is electric field. On a dielectric material, if you apply the electric field, then it will have the surface charges, which is an output. Both belong to the same domain, that is electric domain, and which are related by permittivity and conductivity. So we understand if both the input and output belong to the same domain from the mechanical domain, so we call the materials like steel, aluminum, other materials, no, alloys, they are conventional materials. But imagine when we apply the stress, this material is going to produce the piezoelectric effect. That means when we apply the stress, the material produces surface charges. Then the material is no longer called as a conventional material. We give a specific name as a smart material. Okay, so later on we introduced that. Before that, we just called as a piezoelectric material. So when apply stress, we get a charge. Then it is a piezoelectric. It is a smart material. Similarly, you can see when we apply heat. Okay, so we get a pyroelectric effect. Then it is a smart material. Now you would have figured it out. The materials which are falling along the diagonal direction, they are the conventional materials. Off diagonal materials, either above or below, they are the unconventional materials. Okay, one second. And here uh, you can see two boxes are given here. A box made of continuous line, the other box made up of that means with the boundary dashed one. So this behavior is used for actuation purpose, whereas this behavior which are uh, bounded by the dashed lines, these properties are used for sensing applications. So we understand this slide demonstrates how we call a material as a conventional material, and when we call a material as a smart material, and then what are the properties exclusively used for sensing application, what are the properties used for actuation applications. All those things are clearly demonstrated in this single slide. So what we are going to use for our talk, the example I mentioned at the beginning, no? So the example to demonstrate the application of a polygonal finite element is taken from the this group, which is a shape memory alloy. So uh, that that's what we are going to see. And then we are going to see the piezoelectric material also. So the piezoelectric material is like a stress and then charge current. So it falls over here. Now, quickly we see the shape memory alloy and then we move to piezoelectric material. So, some of you would have come across this word shape memory alloys, which is a nickel titanium alloy. It's a combination of nickel titanium. And on heating, what happens is it will be contracting rather than expanding, it will be contracting. So, if you take a rod made of steel, on heating, it will expand, it will not contract. All of us know that because the atoms no, they will be expanding. But interestingly, if you take a shape memory alloy, on heating it will be contracting. So then if we allow it to cool, then it will expand. So this is a surprising behavior of the shape memory alloys, because it gets its behavior from the microstructure. So here you see our intention is not to go in detail about the microstructure of shape memory alloys, but just to quickly understand how this behavior is happening, you see that the shape memory alloy will have two types of microstructures. One is austenite here, which is shown on the right side, and the other is martensite. So austenite means at a higher temperature, it will be having a higher symmetric crystal structure, which is austenite. At lower temperature, it has a martensite. There is twinned crystal structure. So here you see there are four along the x-axis. You see temperature is given. That is, let us take initially the austenite phase at a higher temperature, and then on cooling, what happens? It is going to move. The temperature keeps decreasing. When it comes to a particular temperature, ms, the martensite structure will start coming into picture. So far from here to here, it was consisting only austenite crystal structure, but the moment it comes to this temperature, the martensite, twinned martensite structure will start appearing in the grains. So further reduction in the temperature will cause increase in the martensite and a decrement in the austenite. So by the time it reaches MF, that is martensite finished temperature, it would have been completely transformed into a martensite only structure. So on heating again, the reverse process will happen, but not with respect to MSMF, but with respect to ASAF. So when it comes to here, the austenite will start appearing in the crystal structure. By the time it goes to AF, it would have been completely transformed into austenite. So these transformations, this is responsible for the uh, uh, like decrement in the length on heating and expansion on cooling. So here, and not only the temperature but also stress can induce this change of crystal structure. So here you see what we have seen in the previous slide is only from these two, that is austenite and martensite twinned. But at constant temperature also we can apply the load so that it can be the microstructure can be converted into austenite to martensite, that is detwinned martensite. On releasing the load, it will come back to its austenite. So at constant temperature also this process can be introduced, but one difference is by reduction in temperature only, if you want to change the crystal structure you will get twinned martensite, whereas at uh, constant temperature, or it could be varying also, no problem, but um, from the austenite, by applying load only we can convert into martensite, but that is called a detwinned martensite. These three crystal structure is responsible for the peculiar behavior of the shape memory alloys. So here on the left side we see the stress strain diagram for a conventional material, like you take a ductile material. Okay, so you know the stress strain curve of them by using offset method, or you can get it if it is not going to give the clear elastic limit. But whatever be the case, you see when the material is taken to the plastic region, the point 3 represents the plastic region is like introduced in the material. So on unloading, it will come back here. You get some plastic strain. Okay, again, loading means it will follow the same path. We know that some residual strain, which is the plastic strain, is given in case of conventional elastic material. On the right side, what we see is the stress strain diagram of a shape memory alloys. So what happens? You see, it goes on loading, it will go here, and then further increment in the load will cause it to transform like this. That means a huge variation in the strain, okay, which is taken along the x-axis. No strain is possible for a small increment in the stress, but on releasing the load it will come back to its original point, but not on the same path through which it moved up, but on a different path. So what you get is an area here. All of us know the area in the stress strain diagram is the energy. So loading and unloading will cause some energy to be dissipated in the form of heat. So here what happens, it can be used for energy absorption. That's why you see that shape memory alloys are used in the uh, during earthquake to absorb the shock, and in many places wherever you want to dissipate the energy. And it is primarily used for actuation applications, and to a certain extent sensing applications also. So you can see here just one small wire would be sufficient to lift a weight. How is it possible? There is a shape memory wire goes along the U shape, and it is being heated up. So by using some external electrical sources, we can allow the current to pass through it. So as the current passes through it, it will, due to resistance, it will get heated up. On heating, it is going to contract. On contracting, it is going to actuate the U clamp. That means the jaws coming closer together so that it will be lifting up. To release it, just stop passing the current through that so that it will be falling down. That means you can unclamp it. So a simple mechanism, instead of using robo or any other thing, we can achieve this. Similarly, here you take a shape memory alloys means here the interesting part of the material is it can remember its shape. That's why it has been given that name. So here, this is the what you see is the actual one. Now you disfigure this, and then you heat it up. how do you heat? Allow the current to pass through it. Otherwise, you immerse in a hot bath. So here it is immersed in the hot bath. Immediately it remembers its original shape, and then it goes back to that shape. So now see, it is immersed. Immediately it remembers its original shape. That is the first shape, and then it goes there. Similarly, it is used for various applications. You can some of you might already known, and others now you can google it and then you can see, because several videos also you can find out. It is used, for example, you can make the Land Rover to move with less like the mechanism required is very less. Okay, so it is used to, it is attempted to use for change in the shape of the wings. But the drawback of this is that its response is not as quick as the other smart materials like piezoelectric material. Takes time. That is a drawback. But it is used extensively for stent applications, because here once it is put it in the artery, then it remembers its original shape, and also initially you may expand it with the help of the balloon, but still it can go to the austenite shape and it will stay there forever. In the stress strain diagram we have discussed that the uh, the shape memory alloys in the particular region, after it crosses the elastic region, for small stress it can give large strains. This is the biggest advantage in the dental applications, because in case of steel, if you apply more load means it will be experiencing more force. But here, for the more or less for the same force, we can give longer deformations, elongations of the wire. So there is an advantage. So, and also it's bio compatible nature allows it to be used for various biomechanics applications. Now we are coming to the material of our interest. There is a piezoelectric material, where we see that, as we have seen before, on applying load it will expand. That means on applying electric field, we can make it either expand or contract depending upon how the electric field is applied, whether a positive charge is applied or negative charge is applied on the top. We can see it will be expanding and contracting. This is called piezoelectric effect. The reverse is also possible. That means when we apply the like when we apply the pressure, surface charges will be generated. That is piezoelectric effect, which is used for sensing applications. On the other hand, on applying electric field, it can, or difference in the potential on the surfaces, it will be expanding and contracting, which is called converse piezoelectric effect. Direct and converse piezoelectric effects. And there are various applications for these materials also, like micro nano positioning, precision for piezo fuel injectors also. I think one of the participants is keeping the mic on. Hello. Okay.
Participants,
Uh,
please mute your mics.
yeah. Thank you. Now it
Thank
is.
you.
Yeah. So we see the various applications of piezo actuators are given. One is micro positioning, and then precision movement, miniaturization. See, we can see the small motor that is put in the operation, that is manufactured with the help of the piezoelectric materials. So it is used in the piezo
Sir,
fuel.
one minute, sir. 1 minute, sir. Jayabal,
Yeah.
sir.
Yes, sir.
Sendil Rajan, sir. Sendil Rajan, sir. Please mute your mic. Sendil Rajan, sir.
Okay, he may not be aware of that it is on.
Yes,
Yes,
yes, sir.
yes. It happens, sir. Okay, no problem. You can proceed, sir.
Okay, okay. Continue, sir. Continue,
You
sir.
can. So otherwise, you can call him if you have the number separately, and then you can tell him, sir. Yeah. So here, what we do is this: we have to have material models. Okay. So, for example, if you know a particular person character, and then we can make a decision whether he can be our friend or not. Similarly, when we are when we are given a material, we should know the character of that material, and then we will be able to take a call whether we can use it or not. So, how we are actually characterizing a material is by doing several experiments, but we cannot be doing experiment every time. So what we do, we go for modeling, material modeling. So the coefficients or constants necessary in the material model will be taken from the experiments, and thereafter we can use that model to understand the behavior of the material under different cases. The simplest material model is nothing but sigma equal to E times epsilon. Okay, so that is the simplest model, linear model we have. But when the material is taken to the plastic region, then we have material models like strain hardening, like linear isotropic hardening models or kinematic hardening models are there. We know that. But when we come for complex materials like piezoelectric materials, the material models are very important. Okay, so even in the previous case, you see we use the isotropic hardening and the kinematic hardening model in the like the finite element method, because you would have noticed that I'm not sure whether you have already come across this stage or it will be taught in the phase two, that you have, of course, linear elastic models would have been already implemented, because in the phase one I think that would have happened. So you have sigma equal to E epsilon is here. Is in the uh, numerical method, that is finite element method. Similarly, here we have to develop a material model for the piezoelectric materials, and then that should be applied into the finite element method. So, what we do, we have the uh, why we have to develop the material model is like we can reduce the number of experiments, because we need to conduct the essential experiments to extract the constant, and thereafter we can understand how the material behaves in different environment. So here what we see is actually the behavior of piezoelectric materials. Okay, and here you see what we see here now. The first one is the behavior of the piezoelectric material. In case of steel, we have seen that there will be elastic region and a strain hardening region and so on. But here, for the piezoelectric material, we see the behavior is actually highly complex. You see here. So as we apply the electric field along the x-axis, we take electric field. Along the y-axis, we take the strain. So as we apply the electric field along the x direction, as we increase, you see the response in terms of strain is measured and given over here. So here 0 electric field, you go to the maximum electric field, let's say 2 kilovolts per mm, then you bring back to 0. From here you move to negative side, minus 2 kilovolts per mm, and then you come back to 0. So during that time, the strain of the macroscopic strain of the material is measured, and then you can see it is varying from 0 to 0.35 percentage. So, but how it is moving is, so it is going to move like this. It is really interesting to see that it is exhibiting a butterfly kind of curve. That's why it is called a classic butterfly for the uh, uh, piezoelectric materials. That is response in terms of strain for the applied electric field is actually, this is a converse piezoelectric effect. So what response we get is a butterfly curve. This is used for actuation applications, but it is not entirely used, but only the region shown in the red color. No, so within this region, it is used for actuation applications. Similarly, for sensing application, we take this diagram. When we apply the stress, so here it is interesting that the stress is applied, it is not taken along the x-axis but along y-axis. During that time, the electric displacement measured on the surface, it is measured, it is given along the x-axis. So you see, on applying the load, you see that there is initially some linear response is measured, and then it undergoes like a plastic region, no, in case of conventional material. But here it is somewhat different because the material is not undergoing plastic deformation, but it is going from a piezoelectric material to ordinary material, because it will be losing its piezoelectric behavior. Okay, so but you don't have to worry too much about it, but just understand that this on application of the electric field, the response measured in terms of strain is used for actuation applications, and within this region we operate for the piezoelectric devices. Similarly, for sensing application, on application of stress, the surface charges will change, which is used for sensing application. But actually, if you apply the load, take it to a beyond a level, then it will be losing its piezoelectric behavior. And here, this diagram, the response in terms of polarization for the cyclic electric field is given here. So these two diagrams are the ones which we are going to replicate. So this macroscopic behavior can be mathematically expressed using the tensorial approach as indicated here. So the strain, as you know, that it is a second order tensor, and P, it is a polarization vector. Polarization is nothing but the electric displacement. So for dielectric materials, we can represent the, that means they can be interchangeably used, not for all materials. So what we do, how this peculiar behavior for the piezoelectric materials are coming, like a butterfly kind of curve, is from the microstructure. Already in the shape memory alloys also we have seen the microstructure, but we have not seen in detail. But here quickly we can see. See, before above Curie temperature, Curie, he along with his brother discovered this behavior, that the piezoelectric behavior in the naturally available material like it is given as Curie temperature. Above Curie temperature, the microstructure will be having a higher crystal structure like a cubic crystal structure. Below Curie temperature, it will be having several lower symmetric crystal structures like tetragonal, rhombohedral, like that. So here we are taking a tetragonal crystal structure. What is the difference between these two is, here both the positive and the negative charge centers of the unit cell coincide, whereas here they get separated. That means when they get separated, the charge centers get separated, there will be a dipole moment. It is very similar to two couples. When two couples means two forces which are separated certain distance, when they are acting in opposite directions, we have the moment. So one force times the distance. No, similarly here we have two charges like forces in opposite direction, but here they are charges, one is positive and other is negative, and the distance between them is given. Then it will be producing a dipole moment, which is nothing but the charge times the distance. So here this is a schematic representation of this one. So when it goes like this, that means the charge center, positive charge center goes above, you get one orientation. Below, that means we have three axes, so six directions we have, plus minus axis, y, and so we can have, when the transformation takes place from cubic to tetragonal, it could have any of the six. It will be appearing in the grains in such a way that the energy of the total system is minimized, because we know that always the nature wants to uh, ensure that minimum energy is utilized. So you can see this is the actual photograph taken from the piezoelectric material, and you see the grain. So within a grain you see that this is one grain. Okay, I am just, you can follow the movement of the cursor, and here within that you can see several orientations. These orientations are actually representing a group of unit cells. For example, here you see one type of unit cells are formed together, that is a group or domain. So another forms another group. You can see the charge centers getting separated, no, depending upon the angle by which they get separated. We call it as a 90-degree domain or 180 domain. This is schematic representation of what is observed inside a grain. Okay, so here what we understand is these orientations. For example, we have 6 domains, no. Here domain represents the group of unit cells. Group of unit cells are called domains, and there are 6 domains. Okay, so what we see, why we have to understand this unit cell behavior when we are concerned the macroscopic behavior means, so some materials are exhibiting a peculiar behavior at the microstructural level. So if you are able to understand their behavior at the microscopic scale, then from that we can bring their behavior in the macroscopic level. So here you see, if you know the unit cell behavior, you can get the domain, group of unit cells behavior. If you know the domain, then we can get the grain behavior. One grain behavior, you know, the several grains, that is a polycrystalline behavior of the material. So in a point we have several polycrystalline. So we can understand how this whole material will behave, which can be used for the application. So that is the multi-scale modeling. And here in our case, we start from the grain. So from the, okay, from here we start. But the unit cell behavior is approximated within the grain. So you see, why we have to learn this is, if you take the piezoelectric devices, this is a piezoelectric material, but inside you see there are some plates which are the electrodes, which are made of different material, because ceramics is the piezoelectric material is a ceramic, but the electrode here is a metal. So there will be like crack will be originating here. So if you have the micromechanical models, then it will be easier, or it will be giving more information about when the crack will initiate, or after introducing the crack, how it will be propagating, and so. So for that purpose, this will be helpful. And also, as we have seen before, we are operating in a smaller region of the maximum potential. So whether there is any possibility of increasing the horizons of this one, that is what another advantage we will be getting. So because of these reasons, we have to develop a micromechanical model, and then that model should be incorporated into a numerical framework like a finite element method, and then we can be proceeding. So we understand now why we have to take the microscopic micromechanical model and all. And then what we do now, our intention is to develop a model, material model, that we have not discussed yet. We have seen only where we can, why we need to have the micromechanical model, and then how it could be excuse me, how what are the numerical methods available. Now we enter into the phase 2. So one second, excuse me. So here our intention is to predict the piezoelectric material behavior from the microstructural level. For that we need two things. One is material model, which will be saying uh, when the grain will, grain means inside the grain we have the unit cells. When the unit cells will change their orientations, that will be determined by the material model. And then that material model should be incorporated into a numerical framework like finite element method. So up to this we understand the background. Now we are entering into the numerical approach. These things I will be skipping very fast, because already you have been exposed to these things. Like there is a physical system, and then we have to develop a mathematical model for that physical system, and then this mathematical model should be continuous model, should be converted to a discrete model, that is the finite element method. Then we get the discrete solution. So whenever there is an error, we come back to the particular part and then we correct it. So in that process, we know that there are two approaches. One is variational approach, and which is also called as Rayleigh-Ritz method, and where we have a potential or a functional, which is a function of function, and we want to minimize that functional with respect to the coefficient, unknown coefficients. We will be getting the a value of the unknown coefficients which are of our importance. Another approach is the weighted residual method, wherein we have three approaches: collocation, least squares, Galerkin method. And of the three, Galerkin method is the most famous method because it has certain advantages. And instantly, the Galerkin method and Rayleigh-Ritz method, both of them are giving the same end results. Both have their advantages. But for most of the engineering applications, we prefer the Rayleigh-Ritz method because the construction of the functional is already available as the total strain energy equal to like the total potential strain energy minus work potential. From there, you will be able to get the functional. So the mathematical model, what we discussed before, is like this is a physical body. You take an infinitesimally small element and then apply the forces and the moments. Finally, using the Newton equilibrium equations, you'll be able to get this governing differential equation. So this is a governing differential equation, and you have the domain. Domain means here the length only, and then you have the boundary conditions like displacement boundary condition and the which is also called as essential boundary condition, and then the natural boundary condition, which is the Neumann boundary condition, which is expressed in terms of fluxes. Here the flux is the stress. And then you would have used this finite element equation Ke times U equal to F. This is the final form of the finite element method for the static conditions. And then you know what is element stiffness matrix. This is the simplest possible element stiffness matrix, and U is the displacement vector. F is the force vector. It has two things: one is body force and then surface traction. Right. So these things, and then you would have come across the element types. 1D element is a line, and 2D element means there will be a triangular element or a quadrilateral element or higher order elements also. 3D means tetrahedral and hexahedral elements. And then you would have come across the shape functions and interpolation functions, like for 1D linear and quadratic polynomials from the 1D perspective. From the 2D perspective, you'll be having the shape functions for a triangular element, and then for CST, and then for LST, that is constant strain triangular element and linear strain triangular element, how the shape functions will change. That also you would have come across by now because you're at the end of the phase one of the finite element. So we can take the higher order elements also. For 1D, if you take a linear element, quadratic element, cubic element. For 2D, we have a triangular element, and in between nodes also there is a CST, LST, and higher order elements. For 2D, apart from the triangular element, we have the quadrilateral elements and then serendipity elements, Lagrange elements, all those things also probably you might have been exposed now. Under 3D, we have the tetrahedral elements and then hexahedral elements and then prisms and so on. But our intention is to uh, uh, analyze from the microstructure point of view. So can we use these standard finite elements for our analysis? A question arises in our mind. Why? Because in case of if you want to analyze the grain, of course, which is a three-dimensional entity. So here, if you have a volume, like let us take this one as a 3D volume of the grain in a piezoelectric material, and then we discretize them with the finite element. So in the standard finite element, what we use is a hexahedral element, as you see here. But what we have seen from the picture taken, it is a 2D picture, but we can understand in 3D how it would be. And then we see that a grain is not of a regular shape. So approximating a grain by hexahedral elements seems oversimplified, because you see while using hexahedral element, all the other three sides, let us assume that you want to take one hexahedral element to represent a single grain, finite element ferroelectric grain, that is piezoelectric grain, is represented by a single finite element. What happens on all the other sides? No, you will see there will be adjacent elements or adjacent grains. So every grain is like surrounded by only four grains side by the side, and one on top and the other at the bottom. But in reality, we see that they are irregular in shape and geometry. So instead of using these, what we have introduced is a polygonal finite element. So the same volume is discretized by polygonal finite element. So you can see this is a single finite element, 3D finite element. So you can see that in the standard finite element, we would have understood that beyond 6 phases, it is difficult to go. Hexagonal elements only we can use as a single finite element. But here, the advantage is we can have a single finite element. So this is one of a typical finite element used in the discretization, which is going to be representing a single ferroelectric grain also. Okay, so how this can be achieved? That is what we are going to see, because we are going to use this finite element, single polygonal element as a single finite element, and also it is going to represent a single ferroelectric grain. So the overall discretization is shown here. Now, when we say the polygonal finite element, this is nothing but a Voronoi polygon. And some of you would have come across this Voronoi polygons. In several places, it is used in the data statistics we are discussing. For example, what is the influence of a particular value at a particular position uh, on the surrounding area, that can be known by using the Voronoi polygon, because of course there is some more thing to be added on that. So here we see how to construct a Voronoi polygon from 2D perspective, and it can be extended to 3D also. So in the 2D, what we do here, you see, initially imagine this as a white screen, and you will be having the randomly thrown points. Only the black points will be here. These 5 points are given here. No, here it seems there are 6 points. One at the center. 1, 2, 3, 4, 5, 6 points are randomly thrown. Then we connect each point with the nearest neighbor. So let us take this point. It is connected with the nearest neighbor. So with all the black points, which are randomly thrown points, are connected. Thereafter, this is the connecting line. No, we have to draw a perpendicular bisector. The blue color is a perpendicular bisector for the line joining the two adjacent points. Okay, similarly, this is another line. So this should be this blue line is a perpendicular bisector for this. So you have to extend them. Okay, wherever these perpendicular bisectors are intersecting, we call it as a node, and then terminate the remaining line. So we get this point. Similarly, these two are perpendicular bisectors of these two lines, and they are intersecting here. So this way we construct a polygon. Here it seems a regular pentagon, but in reality it will be of different irregular polygons with any number of sides. But surprisingly, they will have specific properties, like they are convex in nature and so on. You know what is a convex polygon? So it will be having only a convex polygon. It can have any number of sides, and then we use the governing differential equations. No, like what you have already seen, the strain is a gradient of the gradient of the displacement. Okay, there is nothing but u epsilon equal to du by dx, no, from the 1D point of view. So since it is a strain is a tensor, you are expressing using the symbols. So this is the gradient symbol uh, for u on u. E is the negative gradient of the electric potential. So for 1D, if I say, it will be easy for you to understand that E is equal to that minus dou phi by dou x. But for a 3D perspective, it is a vector, so it is given. And then the balance laws, like divergence of stress is zero, which is expressed as delta x dot sigma, and so on. So this is a constitutive equations and boundary conditions. These are already you have known, but the important point what we have to understand is, probably you would have seen the mechanical problem, but this, the kinematic relation, constitutive relation, boundary condition, all are given for a coupled electromechanical problem, because piezoelectric material is a problem that involves both the mechanical and electric domain. So this is a coupled electromechanical problem. Further, the equations are given here. So here you see here the small capital E, small e, h. No, this E is the elasticity tensor, E is the piezoelectric coupling tensor, H is the permittivity tensor, which are given over here. Okay, constitutive tensors and material properties of particular piezoelectric materials are taken. Now we are coming back to the same point. So we have seen that inside a ferroelectric that is polycrystalline grain, this represents a single ferroelectric grain. That is piezoelectric. Ferroelectric and piezoelectric material is a ferroelectric nature, ferroelectric type. That's why you might have seen that I'm using both the words piezoelectric or ferroelectric. Both are same here. I'm because ferroelectric is a general word. Piezoelectric is a subset of this ferroelectric. So here, what we do, uh, this grain is approximated by a Voronoi based polygon element. Okay, so instead of using the standard finite element, wherein we'll be using a quadrilateral element, maximum we will be using a quadrilateral element from a 2D point of view, or hexagonal element from a 3D point of view. But here we are using a polygon of this nature. And how we use it is using the standard finite element. Of course, we will not be able to go beyond hexagonal element. But what tweaking we do in the functional is given here. Like this is the instead of using the functional, we are using a functional called Hillinger-Reichner functional, which is a function of not only the mechanical displacement electric potential, but with respect to stress and electric displacement also. So we are using the Hillinger-Reichner functional. That functional should be minimized with respect to various things. Okay, so for that, what we do, we do the manipulations like integration by parts, balance laws, divergence theorem, all those things we'll be using. And finally, we push the mechanical displacement electric potential from inside to the boundary. Because you see, in case of a triangular element, how we define the displacement, u equal to n1 u1 plus n2 u2 plus n3 u3, like that. In case of hexagonal element, quadrilateral, n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. Okay, so but why we do that is because the displacement is defined inside the element. But what we do, we push that displacement to the boundary, like here, so that you are going to take only the displacement is defined only along the element boundary. So even with the linear interpolation, there is n1 u equal to n1 u1 plus n2 u2, where u1 u2 are the displacements of the ends, that is the corners. So it is becoming a linear element. But inside, the stress will be defined because stress is also an assumed function here. Okay, so what we do, again we do several manipulations here. And only thing is, what we need to understand is not only the mechanical displacement is an assumed function, but also stress is an assumed function. In case if this electromechanical problem is reduced to a simple mechanical problem, there is a difference. In case of standard finite element, what we do, we take displacement as an assumed function, and then using the constitutive relation we get the stress sigma, because u is known, u we find out, and then from u we find out the strain, from the strain we get the stress, and so on. But here, not only the displacement function, but stress is also an assumed function, and then we progress. That is the fundamental difference. So what we do, again several things are there, but it may be too much for you at this stage. Probably after phase 3, if we have completed the phase 1, phase 2, then after phase 3, probably you may take now it may be little early to explain all these things. So what I skip. So here this one explains clearly that in case of mechanical problem, the displacement is defined only on the surface, but the stress is defined inside the element, which is contrary to the standard finite element. Okay, so finally what we do, these are the assumed functions used for the stresses. Okay, so Already this is a 6 by 6, and on top of that we have to this you can construct yourselves, but only thing is that while constructing you have to be careful that it satisfies the divergence laws. That's it. So under rank sufficiency condition are also there. I'm going to skip because these are the things related to the advanced finite. There is a polynomial finite element methods. Okay, so because you know what is a rank sufficiency, how to ensure that. And then there is a model, because I said no, the sigma equal to E epsilon or isotropic or kinematic models are there. No, those models should be taken and that should be incorporated into the finite element. But here I'm going to skip this development of the switching models I developed. Uh, so here, just to tell you the delta epsilon bar n, no, this will tell you inside the grain. So we have seen 6 variants, no, 6 inside a grain there will be 6 domains, and one domain will be converted into another domain due to the macroscopically applied stresses and strains. How this will be transforming from one form to another form is given by this expression. Okay, so this is called evolution equation. Why it is called evolution equation is inside the grain how one domain extinguishes and the other domain evolves at the cost of the extinguishing uh, domains. So that's why we call it as an evolution equations. Okay, so don't worry, just that would be sufficient. Now we are actually stitching everything, like we are making a food, no, we or a biryani, vegetable biryani you take. So you take the rice and then you take the vegetables and then the other ingredients, spicy items, and then we put together. Similarly here, that is what we do here. Here we have three things. One is like the material model that we have not explained in detail, but you understood that the evolution equations we have mentioned, no? So those evolution equations are available with that. They are nothing but material model. That material model is going to be put into the numerical framework, that is the polygonal finite element. So we put it at the grain level. Okay, it is a mesoscopic model. So what we do, let us take a polycrystalline material, and each polygonal finite element represent a single grain in the material, and then in each grain we are there will be a gas points, you know that gas points will be there, and then we are going to introduce the material model in the gas points, and then we are going to see. But macroscopically only we have to apply the boundary conditions, and that's what we do. So here we apply the boundary conditions in terms of the mechanical displacement and the electric potential on all the surfaces, and then we are applying the electric field. So as we apply these boundary conditions, and then every time we slowly increase the load, mechanical load, and as well as the electric field, then inside the grain what will happen? Inside the grain, the unit cells will try to switch, no? So here inside the grain we are giving the units, the 6 domains we mentioned, no, that will be explained in terms of, that will be given in terms of the volume fractions of those domains. Okay, so as a summary, what we do, we apply the stress or electric field on the top of this one, and inside the grain, we see how the how the electric field and the mechanical stress will be coming. And then in the domain switching model, we use the irreversible energy principles. That means dissipation potential and all there. It is similar to the plasticity, but I don't want to explain more. So using that, you can understand how one domain will be switching from one to another. Okay, so that is the evolution equation. From that, we will be getting inside the grain how the piezoelectric coupling coefficients will be changing, how it will be average to the macroscopic responses. So when we do this, we'll be able to get the behavior. Okay, that's what we do. See on the top, the two drawings, no, they are the two figures, no, they are obtained from the experiments for the cyclic electric field. How the responses are measured in terms of electric displacement and strain. This is the classic butterfly, no, what we have seen before. That is without external stress. But thereafter, we apply a constant stress on top of the material and apply the cyclic electric field. Then again, we increase the constant stress and apply the electric field. This way, what happens is the classic butterfly curve gets compressed and moves downwards. This is what we experimentally observe, and that is what we get in the simulation also, because we have taken a micromechanical model, material model that is incorporated into advanced polygonal finite element method at the grain level, and then we simulate it and we get the response, macroscopic responses that collaborates very well with the experimental observations. Similarly, this is in terms of the for the same loading, the measurement in terms of the electric displacement is given here. Experimentally observed, what we get from this combination is given over here. You can see they are collaborating very well. And another test also we did. I'm going to skip this polarization rotation test. And then here you see uh, this is the electric field. For the cyclic electric field, the responses are measured in terms of strain and electric displacement. That's what we have seen before. And in that case, what will happen inside the grains? That is what we see here. So you see the stresses, how the stresses are changing as we apply the cyclic electric field. Okay, so what happens? These strains, they are across the grain boundaries. They are coming in. So due to the crystallographic orientation, different crystallographic orientation, the stresses will be developed inside that, and as they are elongating and contracting, that will be observed here, and this could provide the later it could be extended for the crack problems also. And this is for in terms of a strain and polarization. This is for 2D. For 3D also we did, because the piezoelectric material is having a domain switching behavior inside the grain. The domains can move from one variant to another. 6 variants I told from one variant to another. So you can understand that when one variant to another it changes, it is called a domain switching. So it is a three-dimensional property. So you have to treat it as a 3D element. Then only you will be able to get the very good behavior. So that is what we did thereafter. And you can see the difference between the butterfly curve and this here, and it is not so good, because from 2D perspective we analyzed. When we took it for 3D, it is coming exactly. Okay. So we find out how the stresses will be varying and electric field will be varying inside that element. So this will give us an idea later on when we are going to, because piezoelectric materials, depending upon the combination of the constituents, it will be having a different piezoelectric behavior. So that is also possible to get what will be the macroscope, what will be the maximum piezoelectric coupling coefficient we can get at the macroscopic level by studying from the microscopic analysis also. So whenever we go for a devices, nowadays you can see that the devices, piezoelectric or any device, they are miniaturized as low as possible in terms of its size. So when we reduce the sizes, then what we do, it is better to go for the micromechanical models, or multi-scale modeling approaches will be better. We cannot simply rely on the macroscopic models. From that sense, this will be helpful. So now you would have noticed that though it would have been little early to expose you to an advanced finite element method, but this will give you an idea about that we don't have to stop with the finite element method. This will be acting as a, like, it can induce you to understand, and some of you might be interested in pursuing your PhD, or if you're already a doctorate, you may be willing to ask your scholar to pursue in this direction, like advanced finite element methods, which can be used as a tool for your problem if you're interested in the micromechanical microscopic modeling of the material. So as a summary, we have seen the advanced finite element method, which is constructed based on the Hellinger-Reichner functional. This can be used for coupled electromechanical problem, and then from the it can be used at the micro scale, wherein each polynomial finite element can be used for to represent a grain, and for that we developed a polynomial finite element from a Voronoi based discretization. And then what will be the material model? I have used my own model. You can put it your own model. Even the isotropic hardening, kinematic hardening, those models also you can put it here, and then you can get the macroscopic behavior. So with this, we close the session. Some of my collaborators, advisors, Professor Shivakumar and Arugya Rajan and Andreas Mansell, these were my advisors. So I just thank them. And thank you. If there are any queries or any quick discussions, because 1 hour 15 minutes, no, yeah, exactly it is 1 o'clock and 15 minutes. So I stop here. Over to you, Professor Murugan.
Yes, sir. Thank you, Professor, for a wonderful session. I think we got an idea how to create a advanced finite element and also how to use it or apply it for the application, micro mechanical applications. Participants, if you have any clarification or doubt, you can unmute yourself and ask with the professor. Amos sir?
Yeah, it's thank you, Amos. Thank you, Professor. Only thing is the participants will be getting a glimpse of what's happening at the advanced research, so they can get some idea, and this may be giving an idea about the next two phases, no, the finite element methods, STTP program, so that they can just relate with what we discussed, and probably it could be helpful also, might be helpful. Thank you, Professor Murugan, and
thank you, Professor. Thank you very much.
I can sign up. Best wishes to you and the participants, and for the program also. Bye.
Thank you very much, Professor.